Hello everyone. I have another video for you on how to use CalcPlot3D. This time we are going to look at regions for triple integrals where we would like to use cylindrical coordinates. So again, spherical coordinates is something that CalcPlot3D currently doesn't do, but I am going to talk about one example where our book suggests spherical coordinates, but we could still visualize by using cylindrical coordinates. So I can tell you how to maybe adapt in certain circumstances. So we are going to go to uh, active calculus here. And we're just going to start by looking at number 8. And we're just going to try to visualize this solid. So we're not really going to worry about the integrating part, the evaluation part. We're just going to try to understand what E looks like. It's the solid bounded by the circular paraboloid z equals 4 minus the quantity x squared plus y squared and the xy plane. So you could go straight into the region feature. I think it's helpful to just look at the surface itself and see what's going on. So this is 4 minus the quantity x squared plus y squared. And I'm just going to zoom out a little bit so I can see more of it, see the actual top, and I'm going to make it transparent. So if you want to see the region down below, so obviously like this is our circular paraboloid, and wherever it intersects the xy plane, that's going to be our bottom, so we want to kind of cut it off there. So you could, for instance, go here and go to quick views and just do positive z if you wanted. But it still does show like a little bit under, but this is like closer to what we actually care about. So the main thing that I want to do though is look from above and see what the region looks like down in the xy plane, because that's what I really care about, right, when I'm doing my like first two bounds. So here it looks basically like a circle of radius 2. And we're going to see why by just using some algebra. So the xy plane is z equals 0. So if we just literally set z equal to 0, we're going to get 4 minus, I don't really need the 1 there, the quantity x squared plus y squared. I can then just add that over and get x squared plus y squared equals 4. This is exactly a circle of radius 2. And so I'm just going to rewrite this as r equals 2. So if I want to now graph the region and not just see the surface here, I can go down, add a region. And I don't want to use rectangular coordinates here because this is just a circle, right? Polar is better, so I can just click on rect, change from rectangular to polar. This already has my radius going from 0 to 2, but I do want the whole circle, so I'm going to go from 0 to 2 pi for theta. And down here, I want my top function to be that paraboloid, so 4 minus the quantity x squared plus y squared. And now I'll click enter. So I see the circle here, and if I go up, you can see that this is exactly what I want. If you do want just kind of your default view rather than the first octant, this is what that would look like. So I can zoom back out. And so this is exactly what our region looks like. So it cuts it off at the xy plane. And this just shows you how you can use cylindrical coordinates. So really, it's just the polar part. Unfortunately, CalcPlot3D currently just allows z equals f of xy. So notice I didn't translate this to like 4 minus r squared, which is something I would like to do if I were fully using cylindrical coordinates. But for what you see in the xy plane, you can switch to polar. So this is one example. I'm going to go back to active calculus here and look at this one. So number 9 says use spherical coordinates to evaluate this triple integral, where E is this ball. So this is basically a sphere of radius 4 and then everything inside it, right? So it's a ball of radius 4. Obviously spherical would be best, but you can still do this using cylindrical coordinates. So this is where, again, it might help to see this. So x squared plus y squared plus z squared equals 16 is kind of that outer bound. So If you have z equals 0, then you're just going to get x squared plus y squared equals 16, or r equals 4, right? So I can go back here and go r equals 0 to 4. It's still going to be all the way around. It's the whole sphere, so 0 to 2 pi. The big difference is going to be my bottom and my top. So this is purely for visualization, right? For bounds itself, like you're going to not have z bounds, obviously, if you're doing spherical coordinates. But you can solve for z. So here, this would give us z equals plus or minus the square root of 16 minus x squared minus y squared, if you solve for it. And so our top part would be 16, or sorry, the square root of 16 minus x squared minus y squared. And the bottom would be negative the square root of that same thing. And there you go, right? So you actually can still get a sphere. I'm going to get rid of this. You can still get your sphere if you don't like how, I don't know, squarish some of it is. You can do more grid lines, like, I don't know, 21 and 45 will probably be better than 11 and 25. And there you go, it rounds it out a little bit. But this is a way you can still deal with this sphere and at least visualize what's going on in cylindrical coordinates. But again, it's not going to help you with your actual bounds for a triple integral in spherical coordinates. Okay, so hopefully that helps, and that's all I've got for you. So thank you for watching.